Okay, let's do one final example. The beauty of this example is it actually has a nice answer, as in it's rational, as opposed to our previous answer. The one answer that we were able to get was an irrational answer, and the others we found numerically because they didn't have antiderivatives that we could work with or find. So let's use this problem here. It doesn't look like it would be a nice one, but it is, right? So step one, we need to find dy dx. So let the formula guide you. Find dy dx first, do it in all of this in little pieces. So you will have x squared as your first, the derivative of the first term. And if you think of that as 1/4 x to the -1, you end up with -1/4 x to the negative 1/4x squared, which is 1/4 x to the -2. So that's the algebraic form of it. And like I said, we often want to clean this up algebraically before we do something like square it. So if we were to multiply or get a common denominator, I should say, of 4x squared, the second term already has that denominator, but the first term needs the 4x squared in it, so it becomes 4x to the 4th. It will be easier to square that than the original expression. So let's work with the rational form of it in blue, and we'll square result we just got. And this is going to get a little bit ugly. The numerator will be 16x to the 8th power minus, since you're going to have a perfect square, it will be 8x to the 4th plus 1. When you square out 4x to the 4th minus 1, that is what you get. When we square the denominator, we have 16x to the 4th. Okay, so that's the square of everything. Okay, now there's a reason this is going to be so nice. It's this minus 8x to the 4th part. They've rigged the problem to be really nice because in step 3, we need to add 1. So we're going to take the answer we had and add 1. So let's write out the answer we had and let's figure out why adding 1 is so nice in this case. If instead of adding 1, I consider the denominator 16x to the 4th, I'm really going to add 16x to the 4th to the numerator. So what that's going to do is it's going to take the negative 8x to the 4th. When we add this on, it's simply going to become positive. So we had a perfect square in this step. After we finish this step, we will again have a perfect square. And we're going to need to take a square root in step 4. So having a perfect square makes for a very nice problem. So this becomes 16x to the 8th plus 8x to the 4th. I'll write that more neatly. Plus 1 all over 16x to the 4th. All right, and I'm going to rewrite this as a perfect squares right now. In fact, I'm going to rewrite the whole thing. The numerator is the perfect square of 4x to the 4th plus 1, and the denominator, that's easier, that's 4x squared, is its square root. Therefore, the whole thing can be written the way I just wrote it. All right, so step 4 now will be easy. Okay, so step 4 leads to a very nice answer. Step 4 is take the square root. So the square root of dy dx squared plus 1 is simply going to be 4x to the 4th plus 1 over 4x squared. All right, now for doing calculus, this is actually not the best way to write the answer. For doing calculus, I want to write that as x squared plus 1 over 4x squared. That's easier for doing the calculus. So now I'm ready for step 5. The length is simply the integral from, I believe we were going from 1 to 2. By the way, again, we don't want to put 0 in because we can see the derivative will not be defined at x equals 0, which is why the problem goes from 1 to 2. So when we put in the integrand, that's going to be, let's put it in parentheses, x squared plus 1 over 4x squared, all integrated with respect to x. Now we can find the antiderivative of each of those terms relatively easily. Although I think it might be easier, let's do this. Let's make this 2 different integrals so that we have 2 simpler problems to work with. In fact, let's put the 1/4 out in front. I think it'll make it even more obvious now that we've broken it up into 2 problems. Okay, so now the antiderivative of x squared, we have seen a number of times, x cubed over 3. We'll evaluate that at 1 and 2, plus 1/4. Now this is integrand is x to the negative 2. So we'll raise that 1. It will become x to the negative 1 over negative 1. That will be the antiderivative. So we have an antiderivative, which will create a minus sign here. Oops, the antiderivative is negative 1/4. 1 over x, evaluate it at 1 and 2. So we get the extra negative sign, and the power of x becomes negative 1, which we write as 1 over x. This is easy to evaluate now. This becomes 8/3 minus 1/3 for the first one, minus 1/4, and then we have 1/2 minus 1. So let's simplify this. We have 7/3 minus 1/4. If we take 1/2 minus 1, we have negative 1/2. So that's just 7/3 plus 1/8. So if we keep on going, oops, sorry about the keyboard there, we need a common denominator of 24, and that would end up being 7 times 8 is 56, plus 3 is equal to 59 over 24. So we ended up with an answer that's not terrible. As a decimal, that's not a great answer, but it is rational, even though it has a very large denominator, and it is a rational answer. So this is an exact answer. So there are times with just the right kind of problem that you can find exactly what the length of the arc is, but it's rare, and the problems that will show up in calculus books where they want you to get exact answers. So you'll see one like that on the homework.